Hello there, and welcome to the Sleepy Library. Tonight, we are drifting into the green embrace of forests, where towering trees stand as ancient sentinels and the forest floor hums with invisible life. These magnificent realms of leaves and bark in shadow are not just collections of plants. They are living, breathing worlds that have shaped our planet for hundreds of millions of years. From the whisper of wind through canopies to the silent conversation happening beneath the soil, forests hold mysteries both grand and minute. They are places where time moves differently, where a single tree might witness the rise and fall of civilizations, and where microscopic organisms labor in darkness to sustain life above. This is not just a journey through woodland. It is a journey into wonder, into the hidden architecture of Earth's green lungs, and into the quiet intelligence that connects all living things beneath the forest floor. The things we will discover are not only strange, but beautifully real. These green cathedrals might challenge what we think we know about intelligence, communication, and the very nature of community. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night settle around you. Allow your mind to grow quiet like a forest at dusk, and let us begin. Forests cover about 31% of Earth's land surface. Imagine that. Nearly a third of all the dry ground on our planet is carpeted in trees. That represents just over 4 billion hectares, an expanse so vast it defies easy comprehension. These green oceans stretch across continents, from the frozen boreal forests that circle the Arctic to the steaming rainforests that straddle the equator. Each forest is unique, shaped by its climate, its soil, its history. Yet all forests share something fundamental. They are communities. Not random assemblages of individual plants competing for survival, but interconnected networks where cooperation often matters more than competition. The forests we see today are the latest chapter in a story that began more than 400 million years ago, when the first primitive forests appeared on land. Since then, forests have shaped the very air we breathe, the water that flows through our rivers, the climate that makes life possible. They have survived ice ages and meteor strikes, adapted to continental drift and volcanic eruptions, and they continue, quietly, patiently, to sustain the world. A single teaspoon of forest soil contains more living organisms than there are people on Earth. Let that thought sink in as you settle deeper into rest. In that tiny measure of Earth, smaller than a sugar cube, there exist billions of bacteria, up to 1 million individual fungi, hundreds of thousands of protozoa, and several hundred nematodes. These organisms are so small they are invisible to the naked eye, yet their importance to the ecosystem is enormous. They form complex food webs in the darkness, with larger animals feeding on smaller ones, bacteria breaking down organic matter, fungi threading through the soil in vast networks. This astonishing diversity of underground life is arranged into communities as intricate as any city, with different species occupying different niches, different roles, different neighborhoods in the soil. A cubic centimeter of forest soil can harbor more than a kilometer of fungal hyphae, those thread-like cords that run through the earth forming mycelia. The soil beneath a forest is not dead dirt. It is a living universe, teeming with activity we cannot see, but upon which all visible life depends. Trees communicate with each other through an underground network of fungi. This discovery has revolutionized how we understand forests. Scientists call these connections mycorrhizal networks, formed when fine, hair-like root tips of trees join together with microscopic fungal filaments. The fungi spread through the soil like a web, connecting individual plants together across vast distances. Some researchers have dubbed this the Wood Wide Web, a name that captures both the wonder and the function of these underground highways. Through these networks, trees can share water and nutrients with their neighbors. They can send warning signals about insect attacks or disease. They can even recognize their relatives and adjust their behavior accordingly. The network allows resources to flow from healthy trees to struggling seedlings, from sunlit canopy giants to shade-dwelling saplings. Older trees, called mother trees by researcher Suzanne Simard, who discovered much of this phenomenon, form the hubs of these networks. A single mother tree can be connected to hundreds of younger trees, passing on carbon, nitrogen, water, and perhaps even chemical information. When a mother tree is wounded or dying, it increases the flow of resources to its offspring, almost like a final gift. The fungus acts as a mediator in this exchange, taking about 30% of the sugar that connected trees produce through photosynthesis as payment for its services. It is a relationship hundreds of millions of years old, a partnership between kingdoms of life that allows forests to function not as groups of individuals, but as superorganisms. The oldest known living tree is nearly 5,000 years old. High in California's White Mountains, in a protected grove where the air is thin and the winds are fierce, grows a Great Basin bristlecone pine called Methuselah. This tree germinated around 2832 BC, making it older than the pyramids of Egypt, older than written language, older than most of human civilization. When Methuselah was a seedling, people were just beginning to smelt bronze, to build the first cities, to develop agriculture beyond simple farming. The tree has stood through every empire, every war, every human achievement and catastrophe. It survived because of, not despite, the harshness of its environment. At elevations between 9,500 and 9,800 feet, where soil is scarce and winds are relentless, the tree grows incredibly slowly. This slow growth produces dense, resinous wood that resists decay, insects, and disease. In very old bristlecone pines, often only a narrow strip of living tissue connects the roots to a handful of live branches. The rest of the tree may appear dead, twisted, and weathered into sculptural forms by centuries of wind and ice. But that thin line of life endures, drawing water up from deep roots, producing needles, making seeds, continuing a story that began when our ancestors were still learning to write on clay tablets. The exact location of Methuselah is kept secret to protect it from vandals, but it stands somewhere in that grove, gnarled and ancient, a living bridge to the deep past. Forests are home to 80% of the world's terrestrial biodiversity. This means that in those green expanses covering just under a third of Earth's land surface, 4 out of every 5 land-dwelling species make their home. The number is staggering when you consider how many species that represents. Forests shelter approximately 80% of amphibian species, creatures that need both water and forest cover to complete their life cycles. They provide habitat for 75% of bird species, from tiny hummingbirds to massive eagles, from forest floor dwellers to canopy specialists. 68% of mammal species live in or depend on forests, from shrews smaller than your thumb to elephants and great apes. Beyond these visible animals, forests harbor countless insects, fungi, bacteria, and other organisms. Many of these species exist nowhere else on Earth, found only in specific forest types or even individual groves. When a forest is destroyed, these endemic species face extinction, their entire world vanishing beneath chainsaws and fires. The richness of life in forests creates complex webs of interaction. Predators depend on prey, pollinators depend on flowers, decomposers depend on dead organic matter, and plants depend on the animals that spread their seeds. Remove one thread, and the whole tapestry begins to fray. This is why forests are called biodiversity hotspots, places where life concentrates in dazzling variety, where evolution has written its most intricate chapters. Tropical rainforests generate much of their own rainfall through transpiration. Trees are not passive recipients of rain. They actively participate in creating the weather. In the Amazon, for instance, 50 to 80% of moisture remains in the ecosystem's water cycle. Water falls as rain, is absorbed by tree roots, travels up through the trunk to the leaves, and is released back into the air through tiny pores in a process called transpiration. A large oak tree can transpire up to 1,600 liters of water on a single day during the growing season. Across an entire forest, this creates enormous amounts of water vapor that rises, cools, and condenses into clouds. These clouds then release rain, which falls back onto the forest, and the cycle continues. But the moisture doesn't just fall locally. Wind carries the water-laden air hundreds or even thousands of kilometers inland, creating what some researchers call flying rivers in the sky. Through this process, forests influence rainfall patterns far from their boundaries. Deforestation in one region can reduce rainfall in areas hundreds of miles downwind. Scientists have shown that deforestation in the Amazon causes reduced rainfall not just in South America, but as far away as the western United States. The forest is, in a very real sense, a rain-making machine, a green engine that pumps moisture through the atmosphere and distributes it across continents. Without forests, many interior regions would become arid, unable to support agriculture or human populations. The trees seed the atmosphere with billions of particles that help water vapor condense into clouds, making the invisible machinery of the water cycle visible in the form of morning mist and afternoon thunderstorms. A forest's canopy can intercept up to 90% of rainfall before it reaches the ground. Imagine rain falling through layers of leaves, each one catching droplets, slowing the water's descent, allowing it to evaporate back into the air or slowly drip down branches to the forest floor. This interception has profound effects. It prevents soil erosion by breaking the force of falling rain, reducing the impact of each drop from a potential weapon against soil structure to a gentle touch. It creates a more humid microclimate beneath the canopy, keeping the forest floor moist even during dry periods. The canopy acts like a living umbrella, sheltering the understory plants and soil organisms from the harsh impact of heavy rain and the drying effects of direct sunlight. In tropical rainforests, the canopy can be so thick that very little rain reaches the ground during the storm itself. Instead, water accumulates on leaves and branches, then continues to drip down for hours after the rain has stopped, creating a sustained, gentle watering rather than a sudden deluge. This moderation of water flow helps prevent flooding downstream, as water is released slowly from the forest rather than running off all at once. The canopy is not a solid barrier, but a layered structure, with emergent trees rising above the main canopy, the canopy itself forming a continuous ceiling, and below that, the understory and shrub layers, each catching and directing water in its own way. Forest soil can hold up to 20 times its weight in water. The ground beneath your feet in a healthy forest is like an enormous sponge, capable of absorbing vast quantities of water and releasing it slowly over time. This capacity comes from the forest's organic matter, the fallen leaves and decomposing wood and root systems that create a porous, crumbly soil structure. Tiny spaces between soil particles hold water while also allowing air to circulate, creating conditions ideal for plant roots and soil organisms. When rain falls on a forest, much of it soaks into this sponge rather than running off the surface. The water percolates down through the soil layers, filtered and purified as it goes, eventually reaching underground aquifers or emerging in springs and streams. This natural water storage system helps regulate stream flow throughout the year, reducing flooding during wet periods and maintaining water availability during droughts. In agricultural landscapes where forests have been removed, water runs off quickly, causing flash floods during storms and dry conditions between rains. The forest's ability to hold and slowly release water is one of its most valuable ecosystem services, providing clean drinking water, maintaining river systems, and moderating local climate. Tree roots play a crucial role in this process, creating channels in the soil as they grow and decompose, allowing water to penetrate deep into the earth. The mycorrhizal fungi that partner with tree roots also help structure the soil, producing sticky proteins that bind soil particles together while maintaining the pore spaces that allow water infiltration. Forests regulate temperature in their surrounding areas through cooling effects. Stand beneath a forest canopy on a hot day and you immediately feel the difference. The temperature can be 10 to 20 degrees cooler than in an open area just meters away. This cooling comes from multiple sources. First, the canopy provides shade, blocking direct sunlight from heating the ground and lower air layers. Second, transpiration from leaves uses energy to convert liquid water into vapor, and this evaporative process removes heat from the surroundings, much like how sweating cools your body. Third, the forest's dark surfaces absorb solar radiation that might otherwise be reflected back into the atmosphere. Though this absorption is then dissipated through transpiration rather than stored as heat. The cooling effects of forests extend beyond their boundaries. Cities with abundant tree cover can be several degrees cooler than those without, helping to reduce the urban heat island effect, where pavement and buildings create zones of intense heat. Studies have shown that neighborhoods with mature street trees have lower rates of heat-related illness during summer heat waves. At a regional scale, the cooling from large forests can influence weather patterns and temperature distributions across hundreds of kilometers. The temperature regulation forests provide will become increasingly important as global temperatures rise, with forests serving as natural air conditioners that reduce the need for energy-intensive human cooling systems. A mature tree can absorb up to 48 pounds of carbon dioxide per year. Through the process of photosynthesis, trees pull carbon dioxide from the air and use sunlight to convert it into sugars, which are then transformed into wood, bark, leaves, and roots. This carbon becomes locked into the tree's structure, where it may remain for centuries. Over its lifetime, a single tree can store a ton or more of carbon dioxide, removing it from the atmosphere, where it would otherwise contribute to climate change. Multiply that by the billions of trees in the world's forests, and you begin to understand why forests are often called the lungs of the earth. Though this metaphor is not quite accurate, forests don't produce a net surplus of oxygen for the atmosphere because they also consume oxygen through respiration and decomposition. They do serve as enormous carbon storage systems. When forests are cut down or burned, this stored carbon is released back into the atmosphere as carbon dioxide, contributing to global warming. Conversely, when new forests grow or existing forests expand, they pull carbon from the air and help moderate climate change. Different tree species and forest types vary in their carbon storage capacity. Fast-growing tropical forests can store carbon quickly, but may not retain it as long, while slow-growing temperate and boreal forests build up carbon over centuries. The soil beneath forests also stores vast amounts of carbon, often more than the trees themselves hold in their biomass. Protecting existing forests and planting new ones is recognized as one of the most effective strategies for addressing climate change, capable of removing billions of tons of carbon dioxide from the atmosphere each year. The sound of a forest is actually the sound of countless small interactions. Close your eyes and listen to a forest, and you hear a symphony of life. But each sound tells a story of behavior, communication, survival. The rustle in the leaves might be a squirrel gathering nuts, a bird searching for insects, or wind moving through the canopy. The crack of a branch could be a deer stepping carefully through undergrowth. Birdsong carries messages of territory and courtship, with different species occupying different acoustic niches to avoid interfering with each other's communication. The buzz of insects, the chirp of crickets, the croak of frogs. All these sounds represent organisms interacting with their environment and each other. Even the sound of rain falling through a forest tells a story, with the patter changing as drops move from canopy to understory to forest floor. In some forests, you can hear the wind itself moving through different layers of vegetation, creating a layered soundscape. Scientists have discovered that forests even produce sounds below the range of human hearing, as tree roots grow through soil and as sap moves up through trunks under tension. The forest is never truly silent. Even in the depths of winter, when many animals sleep and trees stand bare, there are still sounds: the creak of wood under temperature stress, the whisper of wind through bare branches, the occasional call of a winter-active bird. Each sound is a thread in the vast web of forest life, a reminder that stillness and silence are not the same thing. Forests clean the air by filtering out pollutants and particles. Every breath you take in or near a forest is cleaner than it would be in an open area. Trees act as natural air purifiers, absorbing pollutants like ozone, nitrogen oxides, sulfur dioxide, and particulate matter through tiny pores on their leaves called stomata. These same pores that allow trees to take in carbon dioxide and release oxygen also pull in air pollutants, which are then broken down and stored in the tree's tissues or soil. A single tree can remove dozens of pounds of pollutants from the air each year. Across an entire forest, this filtration service is substantial, improving air quality for miles around. Urban forests are particularly valuable in this regard, removing pollutants produced by vehicles, industry, and other human activities. Studies have shown that neighborhoods with more tree cover have lower rates of asthma and other respiratory diseases, partly because of this air cleaning effect. Trees also capture dust and other particles on their leaf surfaces, preventing these irritants from entering human lungs. After a rain, this accumulated material is washed to the ground, where it becomes part of the soil. Beyond removing pollutants, forests produce compounds called phytoncides, natural chemicals that trees release to protect themselves from harmful insects and germs. When humans breathe in these phytoncides during forest walks, they may experience health benefits, including reduced stress hormones and improved immune function. The forest, in essence, creates an atmosphere that actively promotes health and well-being. Tree roots can extend 2 to 3 times wider than the tree's canopy. What you see above ground is only half the tree, perhaps less. Below the surface spreads an intricate network of roots that anchor the tree against wind, absorb water and nutrients from the soil, and store energy for future growth. The root system can be massive, extending outward far beyond the drip line of the canopy, diving deep into the earth, creating a hidden mirror of the tree's visible structure. Some trees send down a strong taproot that penetrates deep into the soil, accessing water that surface roots cannot reach. Others spread their roots horizontally, creating a shallow but extensive network that captures rain and nutrients from the top layers of soil. Many trees employ both strategies, with deep structural roots for support and water access, and shallow fine roots for nutrient absorption. These fine roots, often thinner than a hair, are where most of the action happens. They branch and rebranch into increasingly tiny structures, creating an enormous surface area for absorbing water and dissolved minerals. Many of these fine roots form partnerships with mycorrhizal fungi, exchanging the tree's sugars for the fungus's superior ability to extract nutrients from soil. The total length of all the roots and root hairs on a mature tree can stretch for hundreds of miles, a vast subterranean system working invisibly to support the visible growth above. When roots decompose, they leave channels in the soil that improve its structure and water-holding capacity, benefits that persist long after the tree itself is gone. A single oak tree can support more than 2,300 species. This number includes the obvious inhabitants: birds nesting in branches, squirrels gathering acorns, insects feeding on leaves. But it extends far beyond those visible interactions. The oak's bark hosts lichens and mosses, small invertebrates sheltering in crevices. Its leaves provide food for hundreds of species of caterpillars, which in turn feed birds and other predators. The oak's flowers produce pollen and nectar for bees and other pollinators. Its acorns are a crucial food source for dozens of mammals and birds, supporting them through lean winter months. Beneath the ground, the oak's roots form mycorrhizal partnerships with numerous fungal species while hosting various bacteria and other microorganisms. The tree's deadwood, when branches fall or the tree eventually dies, becomes habitat for wood-boring beetles, fungi, salamanders, and countless other decomposers. Even the oak's galls, those strange growths induced by certain insects, support their own communities of parasites and predators. An oak tree is not a single organism, but an ecosystem, a living apartment building that provides resources and shelter for thousands of species. This is why ecologists call certain trees, including oaks, keystone species. Their presence or absence profoundly affects the entire forest community. Remove the oaks, and the ripple effects cascade through the food web, affecting species that never directly interact with the tree itself. Forests produce oxygen, but the net contribution to atmospheric oxygen is close to zero. This might seem surprising, given how often we hear forests called the lungs of the earth. The truth is more nuanced and equally fascinating. Trees do produce enormous amounts of oxygen through photosynthesis, converting carbon dioxide and water into sugars and oxygen using sunlight. A mature tree might produce 260 pounds of oxygen per year. However, trees also consume oxygen through respiration, both in their own cells and via the vast communities of microorganisms, insects, and other life forms that inhabit them. When leaves, branches, and entire trees die and decompose, that process consumes oxygen as well. The net result is that mature, stable forests produce only slightly more oxygen than they consume, with the surplus being close to zero. This does not diminish their value. Forests still provide crucial ecosystem services. They store carbon, regulate climate, filter water, provide habitat, and more. The oxygen in our atmosphere comes primarily from phytoplankton in the ocean, accumulated over billions of years when ancient organisms died and were buried before they could decompose. Modern forests maintain the oxygen level rather than adding substantially to it. Still, young, growing forests do produce net oxygen as they build biomass, and forests prevent oxygen-consuming events like wildfires when they are healthy and well managed. The relationship between forests and oxygen is complex, a balance of production and consumption that reminds us how interconnected all living systems are. Forests influence cloud formation and rainfall patterns globally. Trees release not just water vapor, but also tiny particles and organic compounds into the atmosphere, and these substances serve as seeds for cloud formation. Water vapor needs something to condense upon to form the tiny droplets that make up clouds. The particles released by forests, including terpenes and other volatile organic compounds, provide perfect condensation nuclei. This process is most pronounced in large tropical forests like the Amazon, where the forest generates so many cloud-forming particles that it significantly affects regional and even global weather patterns. The clouds formed over forests don't just drop rain locally. Wind systems carry these clouds across continents, distributing moisture to areas far from the ocean. Research has shown that air masses that pass over extensive forests produce more rainfall than those that pass over deforested areas, even hundreds of miles downwind. This has profound implications for agriculture and water security in continental interiors. Areas that depend on rainfall for farming may be relying, unknowingly, on forests thousands of kilometers away to supply the moisture that falls on their fields. Deforestation disrupts this system, potentially causing droughts in distant regions that have no direct connection to the cleared area. The forest's role in cloud formation and rainfall distribution is an example of how Earth's systems are interconnected, how a change in one location can cascade across the globe through atmospheric processes. A hectare of forest soil contains approximately 15 tons of living organisms. That is roughly the weight of 20 cows, but instead of a few large animals, this biomass consists of countless small creatures. Earthworms tunneling through the soil, springtails bouncing through leaf litter, mites smaller than a pinhead, nematodes threading through water films around soil particles, and vast numbers of microorganisms too small to see. Each plays a role in the forest ecosystem. Earthworms pull organic matter down from the surface, aerating the soil and mixing nutrients as they digest and excrete. Springtails and mites break down leaf litter into smaller pieces, making it accessible to even tinier decomposers. Nematodes feed on bacteria and fungi, releasing nutrients that plants can use. The microorganisms, including bacteria, archaea, and fungi, carry out the chemical transformations that make nutrients available, that decompose complex organic compounds, that form partnerships with plant roots. This underground biomass represents an enormous investment of energy and nutrients, a living foundation that supports all the visible forest. The soil organisms create the conditions that allow trees to grow, that maintain soil structure, that cycle nutrients. Without them, the forest could not exist. Dead organic matter would pile up undecomposed, nutrients would remain locked in unusable forms, and soil would lose its fertility and structure. The underground community is as diverse and complex as the above-ground forest, a hidden world that deserves as much wonder and protection. Forests can reduce noise pollution by absorbing and deflecting sound waves. If you have ever walked from a noisy street into a park and felt the sudden quiet, you have experienced this effect. Trees and other forest vegetation absorb sound energy, particularly higher frequencies, through their leaves, branches, bark, and the soft forest floor covered in organic matter. A belt of dense forest can reduce noise levels by 5 to 10 decibels or more, which our ears perceive as a significant decrease in volume. The effect is strongest for sounds in the range of human speech and traffic noise, the very sounds that tend to disturb and stress us. The forest's noise reduction comes from multiple mechanisms. Leaves scatter sound waves, preventing them from traveling in straight lines. Soft soil and organic matter absorb sound energy rather than reflecting it. The complex three-dimensional structure of the forest, with trees at different heights and spacing, breaks up sound waves and creates many surfaces for absorption. Even in winter, when deciduous trees lose their leaves, the bare branches and persistent evergreens continue to provide some noise reduction. This acoustic buffering is one reason why people find forests peaceful and restorative. The reduction in anthropogenic noise allows natural sounds, the rustle of leaves, birdsong, the whisper of wind, to come to the foreground. These natural sounds, operating at different frequencies and rhythms than mechanical noises, have been shown to reduce stress and improve mood in listeners. Forests create not just visual beauty, but sonic sanctuaries, places where the sounds of nature can be heard without the overlay of human machinery. Boreal forests encircle the northern hemisphere in an almost continuous band. These forests of spruce, pine, fir, and larch stretch across Alaska, Canada, Scandinavia, and Russia, forming the largest forest biome on Earth. They occupy about 17% of the world's land surface, a vast green ring around the Arctic. In winter, these forests are silent and snow-covered, with temperatures that can plunge below -60 degrees Fahrenheit. In summer, they transform, with long days of sunlight driving photosynthesis and insect hatches that feed clouds of migratory birds. Boreal forests grow slowly in their cold climate, and their trees may be decades or even centuries old, though they are not as tall as their temperate or tropical cousins. The soil beneath boreal forests is often poor in nutrients, acidic, and underlain by permafrost that prevents deep root growth. Despite these challenges, these forests support rich wildlife communities, including moose, wolves, bears, lynx, and numerous bird species. They also store enormous amounts of carbon, both in living trees and in the deep layer of partially decomposed organic matter that accumulates in the cold, slow decomposing environment. As climate change warms the Arctic, boreal forests are shifting northward, with tree line advancing into former tundra, while southern margins face increasing drought and fire. These changes could release vast amounts of stored carbon, or conversely, increase carbon storage if the forests expand their range faster than they lose it at their southern edge. Boreal forests are critical to global climate regulation, and their fate in a warming world will have consequences far beyond their borders. Mangrove forests protect coastlines from erosion and storm damage. These unique forests grow in the intertidal zone where land meets sea, their roots submerged at high tide and exposed at low tide. Mangroves are specially adapted to this harsh environment, with salt-filtering roots and leaves that can excrete excess salt. Their root systems are extraordinary, often growing above the water level to access oxygen, creating dense tangles that trap sediment and build land. This root structure serves as a natural barrier against waves and storm surges, breaking the force of water before it reaches inland areas. Studies have shown that mangrove forests can reduce wave height by up to 66%, significantly protecting coastal communities from flooding during hurricanes and typhoons. The trees themselves are relatively flexible, able to bend in strong winds without breaking. Beyond storm protection, mangroves prevent coastal erosion by stabilizing sediment with their roots, creating land rather than losing it to the sea. They also serve as nurseries for fish and other marine life, with their roots providing shelter for juvenile fish, crabs, shrimp, and other species. Many commercial fish species spend part of their life cycle in mangrove forests, making these ecosystems crucial for both biodiversity and fisheries. Despite their value, mangrove forests are being destroyed at alarming rates, cleared for shrimp farms, coastal development, and other uses. The loss of mangroves leaves coastlines vulnerable and eliminates critical habitat for marine species. Protecting and restoring mangrove forests provides multiple benefits, from climate protection to fisheries support to disaster risk reduction. Trees can live for thousands of years, but some are mere months old. The lifespan of a tree depends on its species, environment, luck. At one extreme are the bristlecone pines, yews, and giant sequoias that can live for millennia, accumulating growth rings like the pages of a history book. At the other end are pioneer species, trees that colonize disturbed areas and grow rapidly, but live only a few years or decades before being replaced by slower-growing, longer-lived species. In between are the familiar trees of temperate forests, oaks and maples and pines that might live for 2 or 3 centuries if conditions are favorable. A tree's lifespan reflects its ecological strategy. Fast-growing pioneers invest energy in rapid height growth and seed production, reaching maturity quickly but having less durable wood that is vulnerable to decay and storm damage. They thrive in openings created by fire, wind, or human disturbance. But as the forest matures and the canopy closes, they are shaded out by taller, longer-lived species. These climax species grow more slowly, producing denser wood and deeper roots, and can persist for centuries once established. They dominate stable, mature forests where disturbance is rare. The mix of species with different lifespans creates forest dynamics, a constant cycle of growth, death, and regeneration. Even in old-growth forests, individual trees are at different life stages, creating a patchwork of young, mature, and ancient individuals. This age diversity contributes to forest resilience, ensuring that no single disturbance event eliminates all trees of reproductive age. Leaves change color in autumn as trees withdraw nutrients for winter storage. The brilliant reds, oranges, and yellows of fall foliage are not created anew each autumn, but revealed as green chlorophyll breaks down. During the growing season, chlorophyll dominates, masking other pigments present in the leaf. Chlorophyll is expensive to produce, requiring nitrogen and other valuable nutrients. So as days shorten and temperatures drop, the tree begins to disassemble the chlorophyll molecules and transport the recovered nutrients back into the trunk and roots for winter storage. As the green fades, other pigments become visible. Carotenoids produce yellow and orange hues and are present year-round, helping to protect the leaf from sun damage. Anthocyanins create red and purple colors and are produced in autumn in response to bright light and cool temperatures, possibly to protect the leaf during the final weeks of nutrient recovery. The exact timing and intensity of fall color depends on weather conditions, with sunny days and cool nights producing the most vibrant displays. Before the leaves fall, the tree forms a layer of cells at the base of each leaf stem, gradually sealing off the connection between leaf and twig. This allows the tree to shed the leaf without leaving an open wound. Once on the ground, the fallen leaves become part of the forest floor ecosystem, providing habitat for countless small animals and slowly decomposing to release their nutrients back into the soil. The autumn ritual of color and leaf fall is a tree's preparation for winter, a strategic withdrawal of resources to safe storage before the hard season arrives. Forest bathing is a recognized therapeutic practice in some cultures. In Japan, this practice is called Shinrin-yoku, which translates to forest bathing, though it involves no water. Instead, it means immersing yourself in the forest atmosphere, slowly walking and observing with all your senses. Research has shown that spending time in forests can reduce stress hormones, lower blood pressure, improve mood, and boost immune system function. The mechanisms behind these benefits are still being studied, but they likely include the calming effects of nature sounds and sights, the presence of phytoncides and other natural compounds in forest air, the reduction in air pollution and noise, and perhaps simply the break from the demands and stimuli of modern life. Studies comparing forest walks to urban walks have found that the forest provides greater benefits for both mental and physical health markers. Even viewing images of forests or sitting in a room with wood surfaces can have measurable positive effects, though smaller than those from actually being in a forest. Some healthcare systems are beginning to prescribe time in nature as a treatment for stress, anxiety, and depression, recognizing that forests offer medicine that no pharmacy can provide. The psychological restoration that comes from forest exposure may be partially innate, a remnant of our evolutionary past when forests were our primary habitat. Whatever the mechanism, the evidence is clear. Forests are good for human health, not just as sources of clean air and water, but as places of healing and restoration. Tropical rainforests are Earth's oldest living ecosystems. Some tropical forests have existed in similar forms for more than 70 million years, persisting through climate changes that eliminated many other ecosystems. They are remnants of the ancient forests that covered much of the Earth during warmer periods of the planet's history. This long history has allowed the evolution of extraordinary biodiversity, with species filling every conceivable niche, from the forest floor to the canopy, from day-active to night-active, from leaf-eaters to predators to decomposers. The stability of tropical rainforests, their consistent, warm, wet conditions year-round, has created an environment where specialization can flourish. Species can evolve very narrow ecological niches because they do not need to adapt to seasonal extremes. This specialization produces incredible diversity, but also makes many species vulnerable to habitat changes. Tropical forests are characterized by high productivity, with rapid growth fueled by year-round warmth and plentiful rain. Dead organic matter decomposes quickly in the heat and humidity, rapidly releasing nutrients back into the ecosystem. Most nutrients are held in living biomass rather than in soil, which is often poor and thin despite the lush growth it supports. This is why tropical forests recover poorly from clearing. Remove the trees and you remove most of the nutrients, leaving degraded soil that cannot easily support regrowth. The ancient nature of tropical forests, their deep evolutionary history, makes their current rapid destruction even more tragic. We are losing ecosystems that took millions of years to develop, along with countless species found nowhere else on Earth. A forest fire is sometimes necessary for forest health. This seems paradoxical, given the destruction that fire brings. But many forest types evolved with fire as a natural part of their ecology, and some even depend on it. In fire-adapted forests, low to moderate intensity burns remove accumulated dead wood and underbrush without killing mature trees, which have developed thick bark and other adaptations to survive flames. These periodic fires prevent the buildup of fuel that could lead to catastrophic blazes. They also create openings in the canopy where sunlight reaches the forest floor, allowing new seedlings to establish. Some trees, like jack pines and certain sequoia species, have serotinous cones that only open to release seeds after being heated by fire, ensuring that their offspring germinate in the nutrient-rich ash of the burned area, free from competition. Fire also releases nutrients locked in organic matter, making them available to surviving plants. In ecosystems where fire has been suppressed for decades, as in many Western American forests, the accumulation of fuel has created conditions for megafires that burn so hot they kill even fire-adapted mature trees and sterilize the soil. Restoring a more natural fire regime through controlled burns is challenging but necessary for forest health in these areas. Not all forests are fire-adapted, of course. Tropical rainforests and many temperate forests evolved without regular fire, and burns in these areas represent damage rather than renewal. Understanding which forests benefit from fire and which are harmed by it is crucial for effective forest management and conservation. The forest floor is a layer cake of decomposition. Walk on a forest floor and you are walking on time, on layers representing years or even decades of accumulated organic matter in various stages of breakdown. The topmost layer, the litter layer, consists of freshly fallen leaves, twigs, bark, and other plant material, still recognizable as the structures they were when alive. Below that lies the fermentation layer, where fungi and larger organisms begin breaking down the organic matter, fragmenting it into smaller pieces. Here, you might find partially decomposed leaves, the frass of insects, and networks of fungal mycelia. Deeper still is the humus layer, where the original structure of the organic matter has been completely transformed into dark, crumbly material, rich in nutrients. This humus is the result of thousands of decomposers working over months or years to break complex organic molecules into simpler forms. Finally, the humus grades into mineral soil, where organic and inorganic materials mix. The depth and character of these layers vary depending on climate, tree species, and decomposition rates. In cold northern forests, decomposition is slow, and organic layers can be deep. In hot tropical forests, decomposition is rapid, and organic layers may be thin despite high litter inputs. The forest floor serves multiple functions. It moderates soil temperature and moisture, provides habitat for countless organisms, gradually releases nutrients to plant roots, and prevents erosion by covering the soil surface. It is both waste disposal system and nutrient bank, cemetery and nursery, stable structure and dynamic process. Trees are the tallest living things on Earth. The record is held by a coast redwood named Hyperion, standing at 380.3 feet tall, taller than a 35-story building. These giants grow in the fog-bathed forests of Northern California, where mild, wet conditions allow for extreme height. But height has costs. Moving water from roots to leaves hundreds of feet overhead requires overcoming gravity and friction in the transport vessels. There appears to be a physical limit to tree height based on the mechanics of water transport, somewhere around 400 feet, beyond which the negative pressure required to pull water upward would cause the water columns to break. Tall trees must also withstand enormous wind forces, requiring massive root systems and structural strength. The tallest trees are not the most massive. That distinction belongs to giant sequoias, which achieve great girth but not the extreme height of coast redwoods. Nor are the tallest trees the oldest. That honor goes to the bristlecone pines. Each tree species has evolved its own strategy, trading off height, width, lifespan, and other factors to fit its ecological niche. The existence of such tall trees demonstrates what is possible when favorable conditions persist over centuries. Hyperion is estimated to be 600 to 800 years old, having grown in an environment free from major disturbance and provided with optimal water, nutrients, and climate. It, and trees like it, stand as living monuments to the power of incremental growth, sustained over vast timescales. Lichens on trees are partnerships between fungi and algae. These organisms that cover bark and rocks in forests are not plants, but symbiotic associations, each partner bringing complementary abilities. The fungus provides structure, protection from drying out, and the ability to attach to surfaces. The alga, or sometimes a cyanobacterium, provides photosynthesis, creating sugars that feed both partners. Neither organism could survive in the same environment alone, but together they colonize habitats like bare rock and tree bark where few other organisms can establish. Lichens grow extremely slowly, some adding only a millimeter per year, but they can live for centuries or even millennia. They are incredibly sensitive to air pollution, particularly sulfur dioxide, and their presence or absence can indicate air quality. In forests, lichens serve several roles. They provide food for various insects and other invertebrates. Some, like the hair lichen that drapes from branches in old-growth forests, create three-dimensional habitat structure. When lichens die and decompose, they contribute organic matter and nutrients to the soil. They also play a role in rock weathering, breaking down stone surfaces and contributing to soil formation over long timescales. The diversity of lichen species in a forest can be astonishing, with dozens or even hundreds of species, each with its preferred microhabitat, some growing on bark, others on rock, some preferring north-facing surfaces, others south-facing, some tolerating deep shade, others requiring more light. Their presence adds another layer of complexity to the forest ecosystem. Forests create their own microclimates. Step inside a forest on a sunny day and you enter a different world. The temperature drops, the air feels more humid, wind speed decreases, and even the quality of light changes, filtered through layers of leaves to a soft green glow. These differences are not merely subjective. Measurements show that forests maintain more stable temperature and humidity than surrounding open areas, with smaller swings between day and night, summer and winter. The canopy provides insulation, shading the forest floor from direct sun in summer and retaining heat in winter. Transpiration from leaves adds moisture to the air, elevating humidity levels. The complex structure of vegetation, from canopy to understory to forest floor, creates barriers to wind, slowing air movement and reducing evaporation. These microclimate effects extend into the soil, where temperatures are more stable than in open ground, important for root activity and soil organism function. The microclimate created by forests allows shade-adapted species, both plant and animal, to thrive. Species that could not survive in the harsher conditions of open areas. It also makes forests more resilient to external climate variations, buffering the extremes of heat, cold, and drought. As global climate becomes more variable and extreme, the microclimate buffering provided by forests becomes increasingly valuable, protecting biodiversity and providing refugia where species can persist, even as surrounding conditions deteriorate. The self-created environment of the forest is both cause and effect of the ecosystem's character, with the trees creating conditions that favor forest species, which in turn maintain the forest structure. Old-growth forests have structures absent from younger forests. These are forests that have developed without major disturbance for centuries, accumulating features that take a long time to develop. Large old trees with thick bark and massive trunks, standing dead trees or snags that provide nesting cavities and foraging sites for birds and mammals. Fallen logs in various stages of decay, serving as nurse logs for new seedlings and habitat for countless organisms. Gaps in the canopy where old trees have fallen, creating patches of higher light and different vegetation. A deep, well-developed forest floor with complex layering of organic matter. Old-growth forests have higher structural diversity than younger forests, with trees of many different ages and sizes, creating a multi-layered canopy. This structural complexity translates to higher biodiversity, as different species find their niches in the various microhabitats. Old-growth forests also store more carbon than younger forests, both in large living trees and in the deadwood and deep organic soils. They provide ecosystem services that second-growth forests cannot fully replicate, including certain types of wildlife habitat and watershed protection. Many species are old-growth dependent, requiring features like large tree cavities or old-growth forest interior conditions to survive. Once old-growth forest is lost, it cannot be replaced quickly. Even if the land is protected and allowed to regrow naturally, it will take centuries for the forest to redevelop old-growth characteristics. This makes the preservation of remaining old-growth forests critically important, as they represent irreplaceable ecological and genetic resources. The deeper we journey into understanding forests, the more we discover connections that weave through every aspect of life on Earth. These are not just collections of trees standing in the ground. They are living libraries of ancient wisdom, chemical factories producing compounds we have barely begun to understand, climate regulators operating on planetary scales, and communities of organisms engaged in relationships of cooperation and competition that mirror our own social structures. Let us continue our exploration into these green worlds, where every fact reveals another layer of wonder. Forests store more carbon in their soil than in their trees. This surprises many people who assume that the massive trunks and branches of trees contain the bulk of forest carbon. But beneath the surface, in the dark soil enriched by centuries of decomposition, lies an even greater carbon reservoir. Forest soils can contain 2 to 3 times as much carbon as the above-ground vegetation, stored in organic matter, plant roots, fungi, and stable compounds formed through decomposition. This carbon has accumulated over long periods, with each year's leaf fall, each fallen branch, each dead organism adding to the total. In boreal forests, where cold temperatures slow decomposition, soil carbon can extend deep into the ground, layer upon layer of partially decayed organic matter, representing centuries of accumulation. In tropical forests, despite rapid decomposition, the constant input of organic matter and the activity of deep-rooting trees maintain substantial soil carbon stocks. The importance of soil carbon extends beyond climate. Organic matter improves soil structure, water holding capacity, and nutrient availability. It supports the vast community of soil organisms that underpin forest productivity. When forests are cleared, much of this soil carbon can be lost rapidly, released to the atmosphere as carbon dioxide as organic matter decomposes or is burned. Protecting forest soils is as important as protecting the trees themselves for maintaining carbon storage and forest ecosystem function. Trees can recognize and favor their own offspring. This discovery has revolutionized our understanding of tree behavior. Research by Suzanne Simard and others has shown that mother trees, those large, old individuals at the center of mycorrhizal networks, can distinguish their own seedlings from unrelated ones, and preferentially send them more carbon through the underground fungal connections. The exact mechanism of this recognition remains mysterious. Trees do not have brains or nervous systems, yet they respond differently to their kin than to strangers. It may involve chemical signatures, scent-like compounds released by roots that allow recognition. Whatever the mechanism, the behavior is clear. Mother trees invest more heavily in their offspring, colonizing them with more extensive mycorrhizal networks, reducing their own root competition near their seedlings, and increasing nutrient transfer when their offspring are stressed. This is not anthropomorphic projection, but documented biological fact. When mother trees are injured or dying, they increase the flow of resources to their offspring even more, as if passing on a final inheritance. This kin selection makes evolutionary sense. By helping their own offspring survive and reproduce, trees propagate their own genes. But it also reveals a level of sophistication in plant behavior that challenges traditional views of plants as passive, unresponsive organisms. Trees are active participants in shaping their environment and the success of future generations. A single large tree can transpire hundreds of gallons of water per day. On a hot summer day, a mature oak tree acts like a living fountain, drawing water from soil, pulling it up through its trunk against gravity, and releasing it as vapor from its leaves. The amount can be staggering, with some large trees transpiring 200 gallons or more in a single day. This water movement serves multiple functions for the tree. It transports dissolved minerals from soil to leaves. It provides the raw material for photosynthesis, and crucially, as water evaporates from leaf surfaces, it cools the leaf, preventing heat damage. The process is driven by solar energy and regulated by the tree through tiny pores called stomata that can open and close to control water loss. During drought, trees close their stomata to conserve water, but this also prevents carbon dioxide from entering the leaf, slowing photosynthesis and growth. The transpiration stream also creates the negative pressure that pulls water upward from roots to canopy, a feat of hydraulic engineering that still amazes plant physiologists. The water released by trees does not vanish. It enters the atmosphere, contributing to humidity, cloud formation, and eventually precipitation. In aggregate, the transpiration from an entire forest represents a massive transfer of water from soil to sky, a green pump that keeps the water cycle moving and influences weather patterns across regions. Forests prevent soil erosion more effectively than any other land cover. Bare soil, exposed to rain and wind, quickly erodes, with topsoil washing away or blowing off, leaving behind degraded land that cannot support plant growth. Forest cover prevents this erosion through multiple mechanisms. The canopy intercepts rain, reducing the impact force of falling drops. The forest floor, covered in leaf litter and organic matter, cushions what rain does reach the ground. Tree roots bind soil particles together, creating a stable matrix that resists being washed away. The roots also create channels that allow water to infiltrate into the soil rather than running off the surface. Even after trees are removed, the effect of their roots persists for years as the root systems slowly decompose. On steep slopes, forests are the only effective long-term erosion control, with terraced agriculture or other land uses being vulnerable to catastrophic landslides during heavy rain. Forest loss has contributed to some of the worst erosion disasters in human history, from the Dust Bowl in the American Great Plains to deforestation-driven landslides in Haiti and other regions. The soil held in place by forests represents thousands of years of development, created through the slow weathering of rock and the accumulation of organic matter. Once lost to erosion, it cannot be quickly replaced. This makes forest protection critical, not just for biodiversity and climate, but for maintaining the productive capacity of the land itself. Tree rings record not just age, but climate history. Each year, a tree adds a new layer of wood just beneath its bark, and the width and density of this growth ring reflects the conditions of that growing season. In good years, with ample rain and moderate temperatures, rings are wide. In drought years, or years with late frosts, rings are narrow. By examining these patterns, scientists can reconstruct past climate, creating records that extend back centuries or even millennia for long-lived trees. Tree ring analysis, called dendrochronology, has revealed patterns of past droughts, temperature fluctuations, and even volcanic eruptions, whose ash cooled the climate and created unusually narrow rings. The technique is so precise that trees from the same region will show identical ring patterns, allowing scientists to match wood from different sources and create master chronologies extending back beyond the life of any individual tree. These records have been crucial for understanding natural climate variability and for placing current climate change in historical context. Tree rings also record other information. The chemistry of the wood reflects atmospheric composition during the year it formed, allowing reconstruction of past carbon dioxide levels, pollution, and even the uptake of nutrients. Rings can reveal fire scars, insect outbreaks, and mechanical damage. They are archives, written in wood, preserving information about the past with annual precision. Seeds can remain viable in soil for decades or even centuries. Forest soil contains not just living organisms and organic matter, but a seed bank, a repository of potential future forests. Seeds fall from trees, are buried by leaf litter and soil animals, and wait for the right conditions to germinate. Some germinate within weeks or months, but others can persist for years. Some species produce seeds with hard coats that protect them from decay, allowing them to remain dormant but viable for extended periods. When a disturbance creates a gap in the forest canopy, allowing light to reach the forest floor, these long dormant seeds can suddenly germinate, sprouting in numbers that seem miraculous given the absence of their parent species from the site. This soil seed bank provides insurance against bad years and allows forests to recover from disturbances. It also complicates forest management and restoration, as the seed bank may contain invasive species or undesirable plants along with native species. The composition and viability of the seed bank changes over time, with some seeds deteriorating while new ones are added. Studies have found viable seeds of certain species in forest soils, decades after the parent plants disappeared from the site. This hidden reservoir of genetic diversity represents potential futures, a range of possible forests waiting to emerge depending on which seeds are activated by changing conditions. Mycorrhizal fungi can extend tree nutrient uptake by a factor of 1,000. The fine roots of trees, thin as hairs, can only explore so much soil. But when those roots partner with mycorrhizal fungi, the effective root system expands enormously. Fungal hyphae are much finer than roots, able to penetrate tiny soil pores that roots cannot reach. They spread far beyond the root system, with a single plant's mycorrhizal network potentially extending for miles through the soil. This vastly increased surface area allows the tree to access nutrients from a much larger volume of soil. The fungi are particularly effective at acquiring phosphorus and nitrogen, nutrients that are often limiting for plant growth. The fungi produce enzymes that can break down organic matter and release nutrients that would otherwise be unavailable. They can also access nutrients from deep in the soil profile, beyond the reach of plant roots. In exchange for this service, the fungi receive sugars from the tree, carbon compounds produced through photosynthesis that the non-photosynthetic fungi cannot make themselves. This partnership is so ancient and so beneficial that the vast majority of land plants form mycorrhizal associations. Trees without their fungal partners grow poorly, or not at all, in most soils. The fungi, in turn, depend entirely on their plant partners for carbon. It is a relationship of mutual dependence and mutual benefit, refined over hundreds of millions of years of coevolution. Forests can continue to influence climate for years after being cut down. The immediate effects of deforestation are obvious: the loss of carbon storage, the release of carbon dioxide from burning or decomposition, the change in surface reflectivity. But the climate impacts persist and even grow for years after the chainsaws fall silent. The loss of transpiration means less moisture entering the atmosphere, gradually reducing rainfall downwind. This can take years to fully manifest as atmospheric circulation patterns adjust to the changed water input. The loss of the forest's cooling effect through evapotranspiration leads to regional warming that persists. The carbon stored in harvested wood products and in disturbed soil continues to be released over decades as these materials decompose. Even the change in surface roughness, from the complex vertical structure of a forest to the smoother surface of agricultural land or regenerating scrub, affects wind patterns and local climate. Some effects work in the opposite direction. Young, rapidly growing forests on deforested land can sequester carbon quickly, though not at rates that fully compensate for the carbon released from mature forest clearing. The full climate impact of deforestation unfolds over decades, making it difficult to appreciate in the moment, but significant when considered over the longer term. Relevant to climate systems. Some tree species require fire to reproduce successfully. These fire-adapted species have evolved reproductive strategies that depend on periodic burning. Some, like jack pines and certain species of eucalyptus, have serotinous cones or fruits that remain closed for years, sometimes decades, until the heat of fire causes them to open and release their seeds. This ensures that seeds are released into a post-fire environment where competition is reduced, nutrients are abundant in the ash, and sunlight reaches the ground. Other species have fire-resistant seeds that can survive in the soil through a burn and then germinate in the improved conditions afterward. Some trees coppice readily after fire, re-sprouting from their root systems even if the above-ground portion is killed. These adaptations allow fire-adapted species to dominate in ecosystems where fire is frequent. In the absence of fire, they may be outcompeted by species that grow faster in the dense shade of an undisturbed forest. Fire suppression in fire-adapted ecosystems has led to major ecological changes, with fire-dependent species declining and fuel accumulating to levels that support catastrophic burns when fire does occur. Restoring natural fire regimes, or using prescribed burns to mimic them, is important for maintaining these ecosystems and the species that depend on them. The air in forests contains compounds that may boost human immune function. When you breathe in the forest air, you are inhaling more than oxygen and nitrogen. Trees release volatile organic compounds called phytoncides, chemicals that help protect them from insects and pathogens. These compounds, which include various terpenes and other aromatic molecules, give forests their characteristic scent. Research, particularly in Japan and South Korea, has shown that exposure to phytoncides can increase the activity of natural killer cells. white blood cells that help fight viruses and tumors. Study participants who spent time in forests showed increased natural killer cell activity that persisted for days or even weeks after the forest visit. Other studies have found reduced levels of stress hormones, lower blood pressure, improved mood, and better sleep quality in people who spend time in forests compared to urban environments. The mechanisms are still being investigated, but phytoncides are one likely factor, along with the psychological benefits of nature exposure, the reduction in noise and air pollution, and perhaps the microbial diversity of forest air. The health benefits of forest bathing have led to its incorporation into public health programs in some countries, with doctors prescribing time in nature as a complement to conventional treatments for stress, anxiety, and other conditions. Deadwood is crucial habitat for thousands of species. When a tree dies, its ecological role is far from over. Dead trees, whether standing as snags or fallen as logs, become vital habitat and food sources for countless organisms. Woodpecker excavate cavities in snags, creating nesting sites that are later used by owls, bats, squirrels, and many other animals. The soft, decaying wood of snags provides foraging grounds for insect-eating birds. Fallen logs create diverse habitats, with different conditions on the upper and lower surfaces, in the loose bark, and in the increasingly decomposed interior as the log ages. Salamanders, snakes, and small mammals shelter in and under logs. Insects, particularly beetles, bore through deadwood, creating galleries and accelerating decomposition. Fungi fruit from logs, sending their spores into the forest. The log itself becomes a nurse log, with tree seedlings establishing on its surface, elevated above the competing vegetation of the forest floor, and benefiting from the nutrients released as the log decays. Over decades, a large fallen tree can support hundreds of species at different stages of its decomposition. The nutrients locked in the wood are slowly released back into the ecosystem, making them available for new growth. Forests, managed for timber production, often remove deadwood, seeing it as waste or fire hazard. But this removal eliminates critical habitat and disrupts nutrient cycling. Maintaining adequate levels of deadwood in various stages of decay is important for forest biodiversity and function. Tropical forests may contain half of all terrestrial species. Despite occupying only about 6 to 7% of Earth's land surface, tropical forests are estimated to contain 50% or more of all terrestrial plant and animal species. The reasons for this extraordinary diversity include the long history of tropical forests, allowing time for speciation and niche diversification, the year-round growing conditions that support high productivity and complex food webs, the structural complexity of tropical forests with their multiple canopy layers, and the relatively stable climate that has allowed specialization rather than requiring broad environmental tolerance. In tropical forests, a single tree may host hundreds of insect species, many found nowhere else. A single hectare can contain more tree species than exist in all of North America. New species are discovered regularly, including not just insects and other small organisms, but birds, mammals, and even large vertebrates previously unknown to science. This diversity makes tropical forests irreplaceable. When they are destroyed, species go extinct before we even know they existed, along with potential medicines, foods, and other resources they might have provided. The pace of tropical deforestation means we are losing species at rates that may rival past mass extinction events. A crisis largely invisible because most of the species being lost are unknown and unnoticed. Protecting tropical forests is crucial, not just for climate, but for preserving the extraordinary biodiversity they contain. Forest restoration can take decades or centuries to achieve full function. Planting trees is relatively quick and simple. Growing a forest is neither. A true forest is more than trees. It is a complex ecosystem with specific soil characteristics, a community of organisms from mycorrhizal fungi to decomposers to pollinators to seed dispersers, a particular structure of canopy layers and gaps, and accumulated deadwood and organic matter. These features develop slowly. Soil improves gradually as organic matter accumulates and soil organisms establish. The seed bank builds over years as mature trees begin producing seeds. Mycorrhizal networks spread slowly through the soil. Deadwood appears only as trees age and die. Forest structure diversifies as trees of different ages and sizes create a multi-layered canopy. Full restoration to old-growth conditions can take 100, 200 or more years, depending on the forest type and the extent of degradation before restoration. This does not mean restoration is pointless. Even young restored forests provide many benefits, including carbon sequestration, wildlife habitat, and watershed protection. But it emphasizes that forest protection is preferable to restoration, as once lost, forest ecosystems cannot be quickly replaced. Successful restoration requires more than planting trees. It requires protecting the site from further disturbance, using diverse native species appropriate to the site, ensuring connectivity to other forest patches that can serve as sources of colonizing species, and often active management in early years to remove invasive species and ensure seedling survival. Trees can chemically defend themselves against insect attacks. When a tree is attacked by leaf-eating insects, it does not passively accept the damage. Trees produce a wide array of defensive chemicals, including tannins that make leaves unpalatable or indigestible, alkaloids that poison or deter herbivores, and volatile compounds that repel insects or attract their predators and parasites. Some of these defenses are constitutive, always present in the tree's tissues. Others are induced, produced in response to damage. When a caterpillar begins eating a leaf, the tree can detect compounds in the caterpillar's saliva and respond by increasing production of defensive chemicals, making its leaves less palatable and slowing or stopping the attack. Some trees can even produce different chemical defenses depending on the specific insect attacking them, a sophisticated response that suggests they can identify their enemies. The production of volatile compounds that attract predators and parasites of herbivorous insects is particularly fascinating. The tree, under attack, essentially calls for help, releasing scent signals that draw in wasps, predatory beetles, and other natural enemies of the insects eating it. There is even evidence that trees can send warning signals to other trees through the mycorrhizal network or through airborne compounds, allowing unattacked trees to preemptively boost their defenses. This active defense system reveals that trees are far from passive, and that the apparent stillness of a forest conceals constant chemical warfare and communication. Bamboo forests can grow at astonishing speeds. Though technically a grass rather than a tree, bamboo grows in forest-like stands and achieves growth rates that seem almost impossible. Some bamboo species can grow more than 3 feet in a single day under optimal conditions, making them the fastest-growing plants on Earth. This rapid growth is possible because bamboo culms emerge from the ground already at their full diameter, then simply elongate, extending internodes rather than thickening as trees do. The energy for this explosive growth comes from extensive underground rhizome systems that store resources accumulated over previous growing seasons. Bamboo forests are ecologically important in many regions, providing food for specialized animals like pandas and bamboo lemurs, and serving as building materials and food for human communities. Some bamboo species have unusual reproductive cycles, with entire populations flowering synchronously after decades of vegetative growth, then dying after producing seeds. This mass flowering, called gregarious flowering, can occur across vast areas, all in the same year, even in bamboo plants that were propagated from cuttings and growing in different parts of the world. The evolutionary advantage of this synchronous flowering is debated, but it may overwhelm seed predators by producing so many seeds at once that some survive despite heavy predation. The rapid growth and strength of bamboo make it valuable for carbon sequestration and as a sustainable building material, with bamboo forests able to be harvested and regrown on short cycles. Forest edges are distinct ecosystems from forest interiors. When a forest meets a field, a road, or another habitat type, the edge zone has different conditions than either the forest interior or the open area. More sunlight penetrates at the edge, creating warmer, drier conditions. Wind can reach further into the forest. These altered conditions favor different plant species, often including invasive plants and early successional species that cannot compete in the deep forest. Some animal species thrive at edges, taking advantage of resources from both habitats. Others, called forest interior species, require large areas of contiguous forest away from edge effects and decline when forests are fragmented. As forests are divided into smaller patches by roads, farms, and development, the proportion of forest in edge habitat increases, while interior forest decreases. In small forest patches, there may be no true interior left, with the entire patch experiencing edge effects. This fragmentation is a major threat to forest biodiversity, as many species adapted to stable forest interior conditions cannot survive in edge-dominated landscapes. The width of the edge effect varies, from a few meters for some microclimatic effects to hundreds of meters for effects on predation, nest parasitism, and species composition. Understanding edge effects is crucial for forest conservation, informing decisions about minimum patch size, corridor design, and protection of large, continuous forest areas. Epiphytes create hanging gardens in forest canopies. In moist forests, particularly tropical rainforests, many plants grow not on the ground, but on the branches and trunks of trees. These epiphytes, including orchids, bromeliads, ferns, and mosses, are not parasites. They do not take nutrients from their host trees. Instead, they use the tree purely as a platform to reach light, gathering water from rain and fog and nutrients from dust, decomposing organic matter and their own shed tissues. Some epiphytes have specialized structures for capturing and storing water, like the tank-forming bromeliads that hold pools of water in their leaf rosettes. These tiny aerial ponds support their own communities of aquatic insects, tadpoles, and microorganisms. The mass of epiphytes in some tropical forests is substantial, adding tons of weight to tree branches and contributing significantly to forest biodiversity. Epiphytes provide food and habitat for many animals, with some species depending entirely on epiphyte resources. Their presence increases the structural complexity of the forest, creating additional layers and niches. They also play a role in nutrient cycling, intercepting nutrients in rainfall and throughfall, and slowly releasing them as they decompose. In some forests, epiphytes account for a significant portion of the photosynthetic activity and biomass, making them important contributors to forest productivity, even though they are not rooted in soil. Trees allocate resources between growth, reproduction, and defense. A tree has finite energy and nutrients to invest, and must balance competing demands. Rapid growth requires resources, but so does producing seeds, and so does defending against pests and diseases. Trees cannot maximize all three simultaneously, leading to trade-offs. A tree in a competitive environment with many neighbors may prioritize height growth to reach sunlight, investing less in lateral growth, reproduction, or defenses. This makes the tree vulnerable to attacks and reduces seed production, but may be necessary for survival in dense forest. A tree in a more open environment may invest more in lateral growth, creating a spreading crown and produce more seeds. A tree under heavy insect attack will divert resources to defensive chemicals, slowing growth. These allocation decisions are not conscious, but result from regulatory systems that respond to environmental cues. The trade-offs change over a tree's lifetime, with young trees prioritizing growth to establish, mature trees shifting toward reproduction once they are large enough to produce substantial seed crops, and old trees maintaining their structure and defenses as growth slows. Understanding these trade-offs helps explain tree form and behavior, and how trees respond to changing conditions. Stressed trees may skip seed production in poor years, conserving resources for survival, then produce mast crops of abundant seeds when conditions improve. Fog drip can provide substantial water input in coastal forests. In regions where fog is common, such as coastal mountain ranges, forests play a special role in the water cycle. As fog drifts through the forest, tiny water droplets condense on leaves, needles, and branches. These droplets coalesce into larger drops that fall to the ground as fog drip, effectively creating rainfall from fog. The amount of water delivered this way can be substantial, in some forests equaling or exceeding normal rainfall, especially during dry seasons when fog is common but rain is rare. This fog drip is particularly important for maintaining stream flow and groundwater recharge during summer droughts. The forest structure affects fog capture efficiency, with certain tree species and forest configurations intercepting more fog than others. Tall conifers with dense needle coverage are especially effective fog catchers. Deforestation or conversion of fog-intercepting forests to other land uses can significantly reduce water availability in the dry season, affecting both human water supplies and aquatic ecosystems. Some communities have recognized this and protect fog forests specifically for their water provision services. The importance of fog drip demonstrates yet another way forests interact with and modify their environment. In this case, harvesting water from the air itself. Animals disperse tree seeds across forests and beyond. Many trees produce fruits specifically to attract animal dispersers. The fruit provides food, while the animal carries seeds away from the parent tree, dropping or defecating them at new locations. This dispersal service is crucial for trees, allowing them to colonize new areas, avoid competition with their own seedlings, and maintain genetic diversity through gene flow between populations. Different trees have partnerships with different dispersers. Some produce small fruits eaten by birds, which may carry seeds for miles before depositing them. Others produce large fruits for mammals like bears or monkeys, which disperse seeds shorter distances, but often to high-quality sites. Some trees have evolved specific relationships with particular dispersers, with fruit characteristics matching the disperser's preferences and capabilities. The loss of seed dispersers can have cascading effects on forests. In regions where large frugivores like elephants or tapirs have been hunted out, large seeded trees decline because their seeds are no longer dispersed. This changes forest composition over time, favoring small seeded species with different dispersal mechanisms. The relationship between trees and their dispersers is a co-evolved partnership, with each partner shaping the evolution of the other. Trees compete for disperser attention through fruit characteristics like color, size, nutritional content, and timing of ripening, while dispersers exert selection pressure on these traits through their feeding choices. Forest floors are highways for fungal networks. Beneath your feet, invisible to the eye, thread the mycelia of countless fungal species, creating networks that can extend for acres. These networks are not passive structures, but active transport systems, moving nutrients, water, and chemical signals between locations. The mycorrhizal networks connecting trees are the most famous, but many other fungi create networks through the forest floor. Saprophytic fungi, those that decompose dead organic matter, spread through leaf litter and soil, breaking down complex molecules and redistributing the released nutrients. Some fungi parasitize other fungi, their hyphae seeking out and penetrating the networks of competitors or prey. The fungal networks create structure in the soil, binding particles together, creating stable aggregates that resist erosion and improve water infiltration. They also modify the chemical environment of the soil, releasing enzymes and acids that break down rock and organic matter, and producing compounds that influence plant growth and microbial activity. The networks are dynamic, constantly growing, dying back, and reorganizing in response to changing conditions. Some individual fungal organisms are enormous, with the largest known organism on Earth being a honey fungus in Oregon, whose mycelial network covers several square miles and weighs hundreds of tons. These hidden networks are fundamental to forest function, mediating much of the nutrient cycling and organism interactions that sustain the forest ecosystem. Forests can recover from catastrophic disturbances. When a forest is destroyed by fire, hurricane, volcanic eruption, or other catastrophic event, it may seem like the ecosystem is lost. But forests are resilient, and recovery often begins remarkably quickly. Seeds buried in the soil or carried in by animals germinate in the disturbed area. Plants resprout from roots or other underground structures that survived the disturbance. Pioneering species, adapted to disturbed conditions, rapidly colonize the site. These early arrivals begin to modify conditions, adding organic matter to the soil, creating shade, and facilitating the establishment of later successional species. Over years and decades, the forest rebuilds, going through stages of succession as different species replace one another. The trajectory and speed of recovery depend on many factors, including the severity of the disturbance, the presence of surviving trees or rootstock, the availability of seeds and dispersers, soil condition, and subsequent weather and disturbances. Some forests can return to pre-disturbance conditions within a human lifetime. Others take centuries or shift to a different, stable state if conditions have changed too much. The resilience of forests to natural disturbances is a product of their evolutionary history. Forests have experienced and adapted to fires, storms, insect outbreaks, and other disturbances for millions of years. However, novel disturbances like invasive species, altered climate, and landscape fragmentation may exceed forests' adaptive capacity, leading to ecosystem transformations or persistent degraded states. Some forests are flooded for part of the year. Floodplain forests, also called riparian or bottomland forests, experience regular inundation as rivers overflow their banks. These forests are adapted to flooding, with trees that can tolerate waterlogged soils and periodic submersion. Some species have specialized root structures, like the knees of bald cypress, that allow oxygen access even when submerged. The flooding brings both challenges and benefits. It stresses trees through oxygen deprivation and physical damage from flowing water and debris. But it also deposits nutrient-rich sediment, making floodplain soils extremely fertile, and it creates diverse habitats, including pools, channels, and wet meadows that support high biodiversity. Floodplain forests provide critical services, including flood control by absorbing and slowing floodwaters, water quality improvement by filtering pollutants and sediment, and wildlife habitat, especially for species that depend on wetlands. They are among the most productive ecosystems on Earth, supporting lush vegetation and abundant wildlife. However, they are also among the most threatened, with many floodplains drained, leveed, or developed. The loss of floodplain forests increases flood risk downstream, reduces water quality, and eliminates critical habitat, demonstrating how human modification of one ecosystem component can have far-reaching consequences. Trees can be grafted together, sharing vascular systems. Sometimes, when two trees grow close together, their roots or branches may touch and eventually fuse, creating a physical connection between the two individuals. This natural grafting can result in shared vascular systems, with water and nutrients flowing between the trees. In some cases, a tree whose trunk has been severely damaged or even cut down can survive indefinitely, kept alive by nutrients received through root grafts from neighboring trees. This creates situations where a stump continues to produce living bark and cambium years after the tree was felled, sustained entirely by its neighbors. Why would trees share resources with non-offspring? The grafted individuals may be genetically related, making kin selection relevant. Or the benefit may be indirect, with the sustained tree providing structural support, wind protection, or other advantages to its neighbors. Root grafts can also transmit diseases and pests between trees, a significant concern in forest pathology. Humans have deliberately grafted trees for thousands of years, creating fruit trees that combine desirable rootstock characteristics with productive fruiting varieties. But natural grafting reminds us that individual trees are not always discrete units, and that the forest is connected not just through soil and air, but sometimes through direct physical unions between individuals. Forests influence wind patterns on multiple scales. At the local scale, forests create roughness that slows wind at the surface, protecting soil from erosion and creating calmer conditions within and immediately downwind of the forest. At the landscape scale, forests can channel winds along valleys and around hills, affecting how air moves across regions. At the continental scale, large forests can influence atmospheric circulation through their effects on heat and moisture. The roughness created by forests affects boundary layer dynamics, the behavior of the lowest few hundred meters of atmosphere, where most weather processes occur. Forests extract energy from the wind, converting it to turbulence that mixes the boundary layer and affects pollutant dispersal, cloud formation, and other phenomena. The cooling effect of forests can create local pressure gradients that drive air circulation, including forest breezes similar to sea breezes, but driven by temperature differences between forest and open land. These local circulations can affect rainfall patterns, with precipitation sometimes enhanced at forest edges where converging airflows lift moisture. Changes in forest cover can alter wind patterns, with deforestation potentially increasing wind speeds and changing erosion, fire behavior, and crop productivity in surrounding areas. The relationship between forests and wind is bidirectional, with forests affecting wind but also shaped by it, as trees adapt their growth form to prevailing winds and wind-driven disturbances like blowdowns influence forest structure and composition. Indigenous peoples have managed forests sustainably for millennia. Before European colonization, many areas regarded as pristine wilderness were actually landscapes shaped by indigenous management practices. These practices included controlled burning to maintain forest openings and promote specific plant and animal species, selective harvest of trees for construction and tools, cultivation of forest plants for food and medicine, and protection of sacred groves and other areas. This management sustained both forests and human communities for thousands of years, maintaining biodiversity while providing resources. The knowledge systems underlying these practices represent sophisticated understanding of forest ecology, developed through centuries of observation and adaptation. Many indigenous communities maintain this knowledge and continue traditional forest management where they retain land rights. Recognizing and supporting indigenous forest stewardship is increasingly seen as crucial for forest conservation, as indigenous territories often have better forest condition and lower deforestation rates than surrounding areas. The false dichotomy between human use and forest conservation is being replaced by understanding that sustainable forest management is possible, and that excluding people from forests may not be the best conservation strategy. Learning from indigenous knowledge and practices can inform modern forest management, offering time-tested approaches to maintaining forests while meeting human needs. Trees communicate through airborne chemical signals. Beyond the underground mycorrhizal networks, trees also communicate through the air. When a tree is attacked by insects, it releases volatile organic compounds into the air, scent signals that can be detected by neighboring trees. These neighbors, receiving the warning, can preemptively boost their own defensive chemicals, making themselves less palatable to the insects before they arrive. This phenomenon has been demonstrated in numerous tree species through careful experiments. The signaling chemicals are specific, with different compounds, released in response to different threats, and the receiving trees respond differently to different signals. The mechanism appears to be an evolved communication system rather than mere eavesdropping, as the quantity and blend of compounds released exceeds what would be necessary for the emitting tree's own purposes. Some of the released compounds also attract predators and parasites of the herbivorous insects, recruiting allies against the attack. The airborne signals can travel significant distances on wind, potentially warning trees far from the initial attack site. However, the effectiveness of this communication is debated, with some researchers questioning whether the concentrations of volatile compounds reaching distant trees are sufficient to trigger responses. The ecological importance of airborne chemical communication is still being determined, but it adds another layer to our understanding of how trees respond to their environment and interact with neighbors. A forest can contain microhabitats with distinct climate conditions. Within the apparent uniformity of a forest exist countless microhabitats, each with its own microclimate. The conditions at the top of the canopy, exposed to full sun and wind, are radically different from those on the shaded forest floor. North-facing and south-facing slopes, though only meters apart, can differ by several degrees in temperature and significantly in moisture. Depressions collect cold air on still nights, creating frost pockets that limit which species can survive there. Boulders, logs, and even individual trees create shade patterns and wind shadows, generating patches of cooler, moister conditions. These microhabitat variations create niches for different species, contributing to overall biodiversity. Some species are microhabitat specialists, found only in specific conditions, like the cool, moist environment of north-facing slopes or the warm, dry conditions of canopy gaps. The mosaic of microhabitats changes over time as trees grow, fall, and decompose, maintaining a shifting landscape of opportunities for different species. Understanding microhabitat variation is important for predicting how species will respond to climate change, as local refugia may allow persistence even as regional conditions become unfavorable. It also complicates conservation planning, as protecting a forest means maintaining not just the dominant trees, but the full range of microhabitat variation they create. Forest fragmentation can create islands of isolated populations. When large continuous forests are divided into smaller patches by roads, agriculture, or development, the remaining forest exists as habitat islands in a sea of unsuitable matrix. Species living in these fragments face new challenges. Small populations are vulnerable to inbreeding, genetic drift, and extinction from random events. Individuals cannot easily move between patches to find mates, colonize new areas, or escape local disturbances. Ratio of edge to interior habitat increases, favoring edge species while harming interior specialists. Fragments may be too small to support wide-ranging species or to maintain viable populations of rare species. The matrix between fragments can be a barrier or a filter, with some species able to cross while others cannot. Over time, fragmented populations diverge genetically, lose species sensitive to fragmentation, and experience ecosystem changes as species interactions are disrupted. However, fragments are not doomed. They can maintain significant biodiversity if they are large enough. If multiple fragments are connected by corridors or stepping stones, and if the matrix is not too hostile. Forest conservation increasingly focuses on maintaining connectivity between patches, allowing movement and gene flow, and on protecting or restoring large, contiguous forest areas that can support the full range of forest species and processes. Carbon stored in forests can persist for centuries in wood products. When a tree is harvested, its fate determines how quickly the stored carbon is returned to the atmosphere. If the wood is burned for fuel or left to decompose, carbon release is relatively rapid, occurring over months to years. But if the wood is used for long-lived products like building timbers, furniture, or other applications, where it is protected from decay, the carbon can remain stored for decades or centuries. Old wooden buildings can hold carbon for hundreds of years. Even in landfills, where conditions are often anaerobic, wood can decompose very slowly, delaying carbon release. This means that sustainable timber harvest, where trees are regrown after cutting, can contribute to long-term carbon storage, with carbon held in both the living forest and the pool of wood products. The climate benefit depends on the forest management practices, ensuring that harvest rates do not exceed growth rates and that forest ecosystems are maintained, and on how harvested wood is used, favoring long-lived products over burning or short-lived uses. Using wood as a substitute for more carbon-intensive materials like concrete or steel can also provide climate benefits, as the energy and emissions required to produce wood are typically lower. The full carbon accounting of forestry is complex, but the potential for wood products to extend carbon storage beyond the life of individual trees is an important consideration in forest climate policy. Nurse logs provide ideal germination sites for tree seedlings. In many forests, you will notice that tree seedlings and saplings grow in lines or clusters on decaying fallen logs. These nurse logs provide advantages over the forest floor for seed germination and seedling establishment. The log is elevated above competing ground vegetation, giving seedlings better access to light. The decaying wood is softer and easier for roots to penetrate than compacted forest soil. As the log decomposes, it releases nutrients directly available to the seedlings rooting into it. The log's moisture-holding capacity provides consistent water availability. Protection from ground-dwelling seed and seedling predators may be better on logs than on the forest floor. Over time, as the log completely decomposes, the roots of the seedlings that grew on it are left suspended or stilt-like, before eventually being buried by new litter and soil. Rows of trees with aligned trunks often indicate they germinated on the same nurse log, which has since completely decomposed. The importance of nurse logs varies among forest types, being most pronounced in wet, temperate forests, where large, slow-decomposing logs are common. Removal of deadwood from forests eliminates these germination sites, potentially affecting forest regeneration patterns and tree species composition, as species differ in their reliance on nurse logs versus mineral soil germination. As you drift further into rest, let the forest images soften in your mind. Think of those ancient bristlecone pines standing silent in the mountains, gnarled and patient, witnesses to thousands of years of human history. Think of the underground networks pulsing with shared resources, trees caring for their offspring through fungal connections we have only begun to understand. Think of the hidden universes in every teaspoon of soil, billions of organisms working in darkness to sustain the green world above. Think of forests regulating climate, creating rain, cleaning air, holding soil in place, sheltering countless species in their layered canopies and complex floors. These green places are not separate from us, but fundamentally connected to human well-being, to the air we breathe, the water we drink, the climate that makes civilization possible. They are ancient and wise, resilient yet vulnerable, generous in their gifts, yet limited in their capacity to recover from damage. As we have journeyed through these facts, we have glimpsed the forest, not as a simple collection of trees, but as a living system of astonishing complexity and beauty. A system that communicates, cooperates, adapts, and endures. A system that sustains us whether we acknowledge it or not. And now, as our journey comes to its gentle close, as your breathing slows and sleep approaches, let yourself feel gratitude for these green cathedrals of our world. Let go of the need to remember every fact, every connection. They will be here when you return. The forests continue their slow work, whether we think of them or not, cycling carbon, producing oxygen, hosting life, shaping weather, standing as they have stood for millions of years. You have done enough for today. You have explored and learned and wondered. Now it is time to rest. Let the forest sounds fade to silence in your mind. Let the green light filtering through leaves give way to the gentle darkness behind your eyelids. Let the complexity and interconnection soften into simple peace. The trees will stand watch through the night. The fungi will continue their silent work in the soil. The forest will breathe, slowly, patiently, as it always has. And you can rest now. Close your eyes. Sink into the comfort of your bed as you would sink into soft moss on a forest floor. Let sleep come as naturally as leaves falling in autumn, as gently as fog drifting through branches. Dream of green places, of quiet growth, of the patient unfolding of seasons. Dream of forests, ancient and new, and let those dreams carry you softly into peaceful, restorative sleep. Good night.